Hello students, today we will discuss about ultrasonic machining. So as we know, ultrasonic machining is one kind of non-traditional machining technique which uses mechanical source of energy to cut or to remove the material from a workpiece, right? So before we start ultrasonic machining, let me give you an idea about ultrasonic, how it can be used for machining. Let us take an example of ultrasonic welding. Before mid-semester, most of you have performed ultrasonic welding in our workshop, right? So same equipment with same tool, maybe sonotrode tape, that can be used for ultrasonic machining by having little modification. So the modification is a minor. So more or less ultrasonic welding and ultrasonic machining are the same thing, but the purpose is different. So in today's sessions, I will brief you about ultrasonic machining, the working principle, mechanism, process parameters, potential applications, and at the end we will discuss about the benefits and the limitations of ultrasonic machining. And at the end we will try to compare the ultrasonic machining over conventional machining techniques such as turning, milling, grinding, drilling, and so on. Okay, so let's begin ultrasonic machining by its basic working principle. So basically in ultrasonic machining, the very important parameter is to generate the ultrasonic waves or energy. So what is ultrasonic waves? So ultrasonic waves are the sound waves with a frequency of more than 20 kilohertz, which is quite high, right? So if I'm able to produce the sound waves at a frequency of more than 20,000 or 20 kilohertz, then it would be called as ultrasonic waves. And these waves can be generated by using a different methods like mechanical, transducer, electronic magnetic wave, thermal energy wave, and so on, right? And the benefit of ultrasonic waves that it can be produced in all three form of medium, that is gases, liquid, and solid. So it can transfer all three mediums. Now principle of ultrasonic machining. So what is the principle of ultrasonic machining? Let us try to have a close look to this diagram of ultrasonic machining. So here you see that the ultrasonic machining consists of ultrasonic tool, which is in form of maybe sonotrode. You can see it's a sonotrode, right, which is made of metal, and this sonotrode is attached to the source of energy that can give you the higher frequency, more than 20 kilohertz. Larger the frequency, more will be the vibrations. So you have a sonotrode, then here you can have this different profile tool of sonotrode, and there is a gap between the workpiece and the sonotrode, right? The workpiece is held through a particular workpiece holder, and this gap is maintained during the machining, and when the machining is happening, it is filled with some abrasive slurry. So it's a liquid which consists of abrasive particles, maybe boron carbide, silicon carbide, aluminum oxide, depends on which type of workpiece material you want to cut. So depending on the workpiece material, we select different types of abrasive slurry, and this abrasive slurry is sent through a nozzle. You can see here it's a nozzle, so it's coming at a set speed, and once you apply this ultrasonic waves, so the amplitude is in this directions, up and down. So your sonotrode, this tool, will move up and down number of times in a fraction of seconds, because the frequency is too high, more than 20,000 hertz, right? So this movement will be very intense in nature, up and down, and during this up and down movement, this abrasive slurry will come into the contact with the workpiece under certain pressure. Which kind of pressure? When this sonotrode is moving upward, then it will apply some forces on this abrasive slurry, and this pressurized abrasive slurry will strike to the workpiece surface, and that is how the material removal will take place, right? So this is the principle of ultrasonic machining. So most important thing is that the tool and the gap between the workpiece and the tool, and finally the abrasive slurry, right? So basically ultrasonic machining is a microchipping or erosion with abrasive particles. Why it's a microchipping or erosion? Because you see that the abrasive slurry basically that removes the material, and the removal of the material is not like in the case of conventional machining that you will see the materials in form of chips or particles like in case of grinding. The rate of material removal, the MRR, would be very small, so it will be a microchipping, right? So that is the difference, and the material is not cut by friction but by erosion. So this abrasive slurry will erode the workpiece surface, and you will have the required machining size and the shape. Also remember that the tool is used here is not following the thumb rule of the conventional machining, right? So unlike conventional machining, the tool is made of softer material than that of the workpiece material, because the role of the tool is not to cut the material, right? The role of the tool here is to what? To apply this high frequency, high amplitude translatory motions to the abrasive slurry, and finally the abrasive slurry will embed it into the workpiece or maybe on the tool itself. So here the tool is not actually making physical contact with the workpiece, so no need to have a harder tool. That's why the tool is used as a soft material from economic point of view. So as we have mentioned that the tool forces, this tool up and down moment forces the abrasive slurries, right? The abrasive slurries are just flowing on the top surface of the tool, right? So this motion that will basically, what will happen, these motions will act as a force on abrasive slurry, and that will impact. Once the force is applied to the abrasive slurry, so this slurry with certain amount of forces value that will impact on the workpiece surface. So this ultrasonic waves to the tool, and the tool upward moment will create a force on the slurry, and the force on the slurry of abrasives will create impact on the workpiece, and this impact will create an erosion of the workpiece material, because these abrasive slurries are very hard in nature. So as I have mentioned that the abrasives may be used for different sort of carbides, oxides, right? Some hard material than the base material or workpiece material. So it can create a huge impact on a workpiece material in order to provide sufficient amount of erosion. So here the metal removal mechanism is erosion, unlike the mechanism of friction in conventional machining. Right? So this is the principle of ultrasonic machining. So same way here the schematic is given. You can say that here that is the ultrasonic machining, that is a bath is given. In bath you can have the abrasive slurries to be filled continuously through nozzle. This is a tool. The tool comes with the transducer, ultrasonic transducers, which can give you the different frequency, but it has to be more than 20,000 hertz. Right? So larger the frequency, the larger the tool moment in a fraction of second. Larger the fraction of second, then you can have the too much vibratory reactions, and these vibratory reactions create a force on this gap, the gap between the workpiece. This is a workpiece, right? This is the workpiece. So in the gap is filled with the abrasive slurry. So the moment will create force on abrasive slurry, and this abrasive slurry impact on the workpiece surface, and this surface gets machined. Same principle, right? The same PPT I have uploaded on LMS Moodle of PDPU, so you can have an access directly to the entire PPT, right? Now here you can see the applications. You can see this is a plastic sample, has an inner groove which is manufactured by ultrasonic machining. You can see there's another plastic sample having this geometry. You see geometry has been manufactured by ultrasonic machining. This is the metal coin. You can see one of the foreign currency coin, that you can see this embossing and grooving of complex nature is done by ultrasonic machining. So these are the applications. So you can find the different applications. Ultrasonic machining can be used for metallic materials, non-metallic materials. So the material is concerned, there is no limitation. Process parameters. Abrasive slurry. So the abrasive slurry basically is a fine abrasive grains, as I have mentioned earlier, right? Having a different materials. A machinist can use its own abrasive slurry, depends on a workpiece material to be cut. So boron carbide, if I have hard material, if I want to cut the steel by ultrasonic machining, I may have to go for boron carbide. But if I want to cut aluminum, I will restrict myself up to maybe aluminum oxide or silicon carbide. No need to go for boron, right? So depends on the hardness of the workpiece, the abrasive slurry is selected. So not only the type of abrasives, but also the size of the abrasives, or we can say grain size, whether to use a coarse grain size, fine grain size. Again, it depends on a type of workpiece material you want to cut. If you are using a larger size, means coarse grain size, then you may have better MRR, but at the same time you may not have that proper surface finish, right? And so on. So depends on the type of material and the type of MRR, that what rate you want to remove the metal, that is decided by grain size after the selection of type of abrasives, right? So this abrasive slurry is having a particular type of abrasive at a particular size of abrasive that erode the workpiece surface. So that is erosion or microchipping is taken place by abrasive slurry with the help of ultrasonic transducers or a tool. So second is a holder. So second parameter is a tool holder and tool. Why tool holder? Because the tool holder basically is attached to the transducer. So here the tool holder basically that transmits the ultrasonic waves to the tool. So it has to be pretty much confirmed that whatever the tool holder you use, right, that must be free from any crack. Because if there is crack in a tool holder, then there is a chance to have a fatigue failure after a certain period of time. Now what is the reason? Because this tool holder translates ultrasonic waves high frequency, so there is a huge intense translatory motion happening in a milliseconds. So if there is a crack developed in a tool holder, then after a certain time there will be a fatigue failure of the tool holder, right? So it has to be pretty much sure that the tool holder should be free from any scratch or any mark or any small or micro crack, right? And the best way is to have the polished smooth surface. Also, tool holder comes with the magnifying tooltip vibrations. So you may see in some of the ultrasonic equipment they come with a booster. So the role of booster in a holder is what? To boost the vibrations at the tool tip. As far as tool is concerned, the tool material must be tough and tactile, right? The tool must be tactile. Normally the medium carbon or low carbon steel or stainless steel in case of corrosive applications. So stainless steel is basically preferred as a tool material, right? The size is a normal size 25 mm long, but it may be varied, depends on your use, your application. And this is the important thing, the mass of the tool should be as minimum as possible, right? So it should not absorb any sort of ultrasonic energy coming from the tool holder. So lighter the weight, minimum absorptions of the ultrasonic energy, and you can have the highest possible vibrations at tool tip here. So you can have the better or enhanced or increased tool tip vibration. Definitely it will help to achieve required material removal rate, MRR. So materials can be machined, all materials, metallic materials, ceramic, right? Even glass also can be machined. Brittle material, there is no issue. So USM has no limitation as far as the type of material is concerned. Applications, you can do all the operations like drilling, grinding, profiling or milling, coining, means embossing, and piercing in dies of metal forming. So the advantages and disadvantages, every coin has a two side. So let us first discuss about the limitation first. So now we have brief idea about the basic mechanism or principle of ultrasonic machining. So disadvantage is that, as you know, that material removal rate is quite low. Tool wear fast because the tool is made of lightweight material having low hardness compared to the workpiece, right? So it wears fast in USM. And second one is the machining area. The machining area, basically the depth is restrained, because depth we cannot control the depth, because here the material is removed through abrasive slurries, right? Not by the tool. And also the area is limited depending on the size of the tool we use. So these two things restrict USM when you are looking for a higher MRR. Now advantages, right? Very important advantage. Any material, whether it's a conductive or non-conductive, that can be machined. Let's take an example of electro discharge machining. In our workshop we have wire cut, EDM, right? So we can cut the material only the conductive by using EDM wire cut. But if I want to cut the rubber, if I want to cut ceramic or glass, it's difficult. It's almost impossible task on EDM wire cut. So USM can take care of all the materials irrespective of their electrical or thermal conductivity. USM is very suitable for machining semiconductor materials like silicon and germanium, right? The semiconductor, you can see that the semiconductor materials popularly used in energy applications. It's energy materials, right? You can see the solar cell. They use a lot of semiconductor materials. So to cut the semiconductor, USM is suitable. Precise machining of brittle material. We know that in brittle material, it is very hard to obtain the dimensional tolerance or surface finish accuracy after machining because of the brittle nature. But in USM, that can be achieved because of the working principle. Then this advantage gives you the idea about the properties of the machined component after USM. So if I do ultrasonic machining, then I do not have to worry about the mechanical property of the machined component. Why? Because there is no electricity produced at the workpiece interface, no thermal degradations or temperature rise happens, there is no chemical abnormal surfacing. So that allows that whatever the machined component is produced by ultrasonic machining, there is minimum or no metallurgical changes happen after machining. So if I want to machine hard material like a super alloy, at a nickel based alloy, right? So if I want to drill maybe a little bit odd size or shape hole, then based on my design of the tool, I can drill very easily any asymmetric hole in a hard materials. And obviously less temperature generation or less heat generation, less stress generated during the ultrasonic machining. So the machined component by ultrasonic machining is free from any metallurgical changes. So these are the advantages, right? So here I am ending ultrasonic machining. So now your role is to go through the ultrasonic machining much more in detail from the book you are referring, right? And try to make the understanding in terms of the process parameters. Just learn all the process parameters with respect to different materials and how it can be influenced, right? So keep on reading the contents, so we should not have any lag for the end semester. Okay, thank you.